Okay, so we are ready to start with our charge balance calculation. I'm going to do this in two parts. We're going to do a little bit here in Excel to get some of the initial calculations in for the sum of the negative charge and the sum of the positive charge without iron. But then I'm going to do a little diversion over to PowerPoint to show you the derivation of the equations to calculate the normalized iron 3 plus and the normalized iron 2 plus. I think this is sort of helpful because rather than just put this rather complex looking equation in there that you may look at initially and go, well, how did he come up with that? If we go through the derivation, you'll see that it's really very sort of logically put together, and I think it'll help you when you end up putting your spreadsheet together. So let's start off from the beginning. I think the first cell that we want to take a look at here is we want to do the sum of the negative charge. Now, normally when you think of an amphibole, you kind of look over here and you see, okay, well, there are 22 oxygens, so that is the equivalent of negative 44 charge. We typically would have two OHs in here, so that would be another -2, so we'd have a total of -46 as our charge, and so we could conceivably just write -46 here. But remember, we talked about the possibility of oxygen also going into the OH site, particularly in an amphibole, for example, like quercitite that we see down here. And so in reality, we may actually end up seeing, rather than a -46, we might see potentially as much as a -48. And so we want to have some way of being able to accommodate this potential variability of the negative charge. And so what we're going to do here, and this is why we spent a little bit of time earlier in trying to do some of the initial site fillings, is that we are going to go over to the OH site and use that as the basis for our calculation of our net negative charge. So I'm going to start here in the sum of the minus charge column, the sum of the negative charge column here, and I'm going to put my equal sign in here. And now we are going to start with, well, let's start with the oxygen first. And so we want a -2 charge, okay, and then we want the amount of oxygen that is actually in the oxygen site, which is right here, okay? And there are 22 of those, and so we can just very simply do -2 times 22. Okay, but now we have to take care of the charge in the OH site, and so we are going to go -1, so this represents the -1 charge that we're going to have, and we want to tabulate the total amount of -1 anions that are in that site. And so I am going to do times, and we are going to head over here to the OH site. And you see that we have two potential -1 anions. We have the OH group, and we have fluorine. Now, again, in some more complex amphibole analysis, we may also have chlorine present, but in this case, we don't. So I'm just going to put my parentheses in here and then add OH and fluorine together. And so this represents the total amount of OH or F that's present, so all of the -1 anions. But we also want to take into account the possibility of oxygen in the site, and so we are going to go -2 times, and then we want to look at the amount of oxygen in the site. So if I hit return here, you'll see that in this case we do get a -46, and of course that's because there is no oxygen in the site. And if I were to copy this formula down to some of these others, we'd probably see -46 as well, because we don't have any titanium in here that may put some oxygen into that OH site. But you'll see that later on when we get down here to the quercitite, that this -46 is going to end up being -48. And then still later on when we do our mystery amphibole, well, we're going to have a number in between -46 and -48. Okay, so we've taken care of the sum of the negative charge. Now we want to take a look at the sum of the positive charge, but we don't want to include iron. And the reason that we don't want to include iron is because we need to figure out still what is the amount of iron 2 plus and what is the amount of iron 3 plus. And because we don't know that yet, we can't assume what it is. So the way that we build this is we're essentially going to just go through and apply the charge of all of the ions in there except for iron. Okay, so the first thing we need to do is we have to keep in mind that because we're balancing this against the normalized oxygens and OHs in the anions, among the anion sites here, that we need to be sure that we are using normalized cations. And so the first thing that I'm going to do here is put the normalization factor in here. Okay, and again, I'll put my dollar sign in the front just to ensure that if I'm copying it around later on that it stays in that cell. And now we're just going to systematically go through. I'm going to put my time sign in here and parenthesis, and now I'm going to start building the total accumulated charge of all of the cations except for iron. So we might as well do this systematically. We will start with the +1 cations, and so I will put a 1 in there, times, and now I'll do another parenthesis, and we will check our list of cations here for all the things that are +1. Now, of course, this is a thing, this is a portion of the spreadsheet where you're going to have to sort of know your periodic table a little bit, know the typical charges of ions that go into that different elements are. So if you're sort of unfamiliar with this, you should pull out your periodic table and study it a little bit, because this is probably one of the main places that kind of messes people up, where they get the wrong charges for various cations. So you'll want to be careful here. But in any case, so the 1 plus cations, well, we have sodium, okay, and we have potassium as our 2 1 plus cations. Okay, so I'm going to close that up there, and now we will do the 2 plus cations. Okay, so I open the parenthesis there, and so now let's go through and do all of the 2 plus cations. Well, magnesium is a 2 plus cation, and calcium is a 2 plus cation, and iron could be a +2 cation, but we don't know, so we are not going to include it in this. So we close the parentheses, and now we move on to the 3 plus cations, and we do the same thing, and in this case the 3 plus cation is aluminum, and again some of the iron may be 3 plus. Now there isn't any iron in this particular amphibole, but in our mystery one later on, some of the iron may be 3 plus, but we don't know how much, so we can't include that. So I will close the parentheses, and then we will do the 4 plus cations, and we have silicon and titanium. And it looks like we've covered all of the cations excluding iron. Okay, now fluorine is an anion, so we don't include fluorine in this calculation. And we don't have any phosphorus present, so we don't need to do the 5 pluses. We don't have any sulfur as sulfate present, so we don't have to worry about the 6 pluses. So in this case, we are done. I'm going to close the parentheses, and there we have a value that of our sum of the positive charge without iron. And you can see that this is extremely close to the original 46. And so what we're probably seeing here is that slight little deviation off of the ideal 46 is probably just rounding error that's going on in here. Okay? So now we need to calculate some additional parameters in here. So we can't do the charge balance yet because we need to have the total amount of charges present. So our next calculation here is going to be the normalized iron 3 plus. Okay, and this is where I'm going to take our little deviation over to PowerPoint and show you sort of how the normalized iron 3 plus and the normalized iron 2 plus cells are calculated. So let's pop over here to PowerPoint. And so now we're going to do the remainder of the derivation for the charge balance equations. Okay, so what are the two unknowns that we want to solve for? Well, we want to solve for iron 2 plus normalized, okay, and iron 3 plus normalized. And I've color coded these. I've kind of color coded them according to the colors that they frequently cause in minerals. And so we have a bit of a greenish color here for iron 2 plus. We have a red here for iron 3 plus. And I'm going to maintain these colors kind of throughout this little PowerPoint presentation in order for you to kind of keep these things well separated. Okay, so let's move on here. If we have two unknowns, we're going to require two equations. Okay, so equation 1 and equation 2. What are these two equations? Well, the first equation is going to have to be a mass balance equation. So let's see how we do this mass balance equation. We know that the total amount of iron 2 plus normalized and the total amount of iron 3 plus normalized has to be equal to something, okay? So what is it equal to? Well, I think if you think about this for a moment, you'll recognize that this has to be equal to the total amount of iron normalized that's available for us to use, okay? So that's the total combination, the total amount of iron that we have available. So what is this total amount of iron that we have available? Okay, what is the sum of iron normalized? Well, we have that already in or we have the ability to calculate that already. And what that is it's the normalization factor times the raw moles of iron. Okay, so we're going to come back to this a little later on. But what we want to do first is we want to look at the next equation. Okay, so the second equation here is going to be the charge balance equation, and we're going to do this one little piece at a time, okay? So the first thing that we have is we just calculated a moment ago the sum of the positive charges without iron. But that isn't all of the positive charge that we have available. We want to accumulate all of the potential positive charge that we have available. So the first thing that we would add, or I guess the full thing that we would add here is we need to add the amount of iron 2 plus and its charge and the amount of iron 3 plus, the charge associated with that. And so you can see that I have a 2 times iron 2 plus and a 3 times iron 3 plus because the 2 times this number here represents the amount of charge that's associated with the iron 2 plus. So for every atom of iron 2 plus, there are 2 charges associated with it. And for every atom of iron 3 plus, there are 3 charges associated in, because remember, we're calculating charge here. That's what we're interested in. We're not interested in the atoms per se. We're interested in the charge. So this entire set here of the sum of the positive charge without iron, 2 times the sum of the iron 2 plus, and 3 times the sum of the iron 3 plus, this represents the total amount of positive charge that we have available. Okay. Now, keep in mind that this is a charge balance equation, so we need to balance this out with something. So in addition to the positive charge, we are going to add the negative charge. Okay, so the positive charge added together to the negative charge, and the negative charge just represents this sum of the minus that we just previously calculated in Excel a moment ago. And in a perfect formula, in an ideal formula, we would expect, if you want to think about what this is equal to, well, the sum of the positives and the sum of the negatives should completely balance out. And so what we should get is that the net should be 0. Okay? So let's look at both of these equations together, because this is fundamentally how we're going to do this calculation. So, sorry about that. I think I went back a couple of things there. So here's our mass balance equation. Iron 2 normalized plus iron 3 normalized equals the sum of the iron. Here's our charge balance equation. Sum of the positives without iron plus 2 times the sum of the iron 2 plus 3 times the sum of the iron 3 plus the sum of the negatives equals 0. Well, now we have 2 equations in 2 unknowns, so we should be able to solve for all to in order to solve this, I'm going to do a little bit of rearranging first to make this a little easier. So what I've done here is I've moved the sum of the positives without iron to the right-hand side of the equation, and I've moved the sum of the negatives over to the right-hand side of the equation as well. So if you sort of look between these two slides here, you'll kind of see essentially what I did. It's just algebra. Okay, so we have these two, we have them set up. So how are we going to solve these equations? Well, there are a couple of different ways that we can do this. Substitution is probably the way that people will typically want to do this, but I find that linear combination is the easiest way to do this. And I'm going to go through an example of how you do linear combination. Okay, so we have both of these equations lined up here, kind of in a nice convenient fashion. And the first thing that we're going to do is we are going to look at the top mass balance equation, and we are going to multiply every single term by -2. So you can see I multiplied this by -2, I multiplied the iron 3 plus by -2, and I multiplied the sum of the normalized iron by -2. Okay, so it turns out that the way this is set up now, we can actually just add both of these equations together. And we're just going to add straight down in each of these sets, and we're going to see what we get. And you're going to like this because this is actually kind of cool. If we add the -2 times the iron 2 plus normalized to the +2 iron 2 plus normalized, well, they cancel each other out, and we get 0. Then when we add the -2 iron 3 plus normalized to +3, or to +3 times iron 3 plus normalized, you see that we have a net of 1 iron 3 plus normalized left over. And then when we add the right-hand side together, well, you see there isn't really any way to simplify that, and so that just becomes all three of those terms. So we have the minus the sum of the negative charge minus the sum of the positive charge without iron minus 2 times the sum of the iron normalized. Okay, and to clean that up a little bit, I'm just going to essentially pretty it up here. And so what we have is iron 3 plus normalized is equal to minus the sum of the negative charge minus the sum of the positive charge without iron minus 2 times the sum of the iron normalized. And again, to use some of our original Excel worksheet cells, I'm just replacing this term up here, the sum of the iron normalized, with the normalization factor times the raw moles of iron. Okay, so let's go back to Excel here, and let's type that formula in here. Now keep in mind, this is again for iron 3 plus. So I'm going to go equals, and if you recall, it's going to be minus the sum of the negative charge, okay, minus the sum of the positive charge, minus 2 times the normalization factor times the raw moles of iron, right here. Okay. So I don't actually know why we have a very small number here. It's probably, again, because of the slight rounding error that we see in here. If this were actually minus 46, I think this would come out to be 0. So within 2 decimal places, you'll see that this is 0, but this is really just a rounding error. I'm not too concerned about it. But we do have to do a couple of additional things on here. So one thing that we need to be careful about is that the calculation for iron 2 plus and 3 plus assumes that the analysis is a very high quality analysis. And in fact, as you can see here, I've got a little bit of an error built in here. But we want to be careful that because all of the error of the analysis is put into this calculation, that we want to have some of the same sort of safeguards that we put in before with regard to, for example, we don't want a value that's a negative number for iron 3 plus. We don't want to have a value of iron 3 plus that's greater than the total amount of iron that we have. And so we put these sort of same safeguards in that we talked about previously when we were doing the tetrahedral aluminum calculation. And so we have this formula here, and we want to ensure that if it's less than 0, that the value here is going to be 0. Okay? And then we set up yet another if-then statement where, again, we look at this entire formula, and I'm just going to recopy it here. We want to know that if this value is greater than the total amount of iron that we have available, and keep in mind again that this is normalized iron, so it's going to be the normalization factor times iron, okay, that if it's greater than the amount of normalized iron, well, it can never be greater than that. It can only max to that value. So I'm going to copy this, and there we have it maxed out. And finally, again, if it is neither less than 0 nor greater than the amount of iron that we have present, then we just want it to be the original equation that we assumed. So I can then just recopy this and put it here at the end. And again, we have two nested if statements, and so we're going to need 2 parentheses to close it off. And you'll see that certainly to 1 decimal place that I have made no iron 3 plus. Okay. Now, because we've already built in these safeguards, we don't have to worry about rebuilding in the safeguards for normalized iron 2. And so the calculation for normalized iron 2 is just going to be the total amount of normalized iron, which again is the normalization factor times the total amount of iron. Okay. And then we are going to subtract out the amount of iron that is already being used up as iron 3 plus. And again, there's no iron in this sample, so we see that both of those values are 0. So we can now take care of our final 2 calculations here. We are curious as to what the iron 3 over total iron ratio is here. Now this is probably going to come out to be a divide by 0 error, but I'm going to set the formula up anyway. And so this will be the total amount of normalized iron 3 divided by the total amount of iron. And yes, we have a divided by 0 error, but again, I'm not worried about that because there is no iron in this formula. You'll see that when we copy this formula down here to the ferrogedrite and then again to our mystery amphibole, that this will ostensibly be a real number. Okay. We have one final cell that we want to take care of in here. We want to look at the overall charge balance. Now, ideally, we hope that the charge balance is going to be 0, but again, because we've built in some safeguards in here, there is always a possibility that this is going to be a slight number, a number that's slightly bigger than 0, or a number that's going to be slightly smaller than 0. And one way to assess the quality of the analysis is to see how close to 0 that number is. If it's 0, there is a good chance that the analysis is actually quite good. It's not a guarantee, but it is a good chance that the analysis is quite good. If the number is, say, within 1% of one of these, and so, for example, if the number is less than 0.4, give or take, then I'd say the analysis is probably still pretty good. Maybe not quite as good as it could be, but probably still pretty good. On the other hand, if this number ends up being something like 5% or 10% of what one of these are, then I'd say that the charge balance is not very good, And there could be a number of reasons for that. It could be that you have a charge of an element that's incorrect. You're missing some elements. It could be that you have the wrong mineral. That perhaps you think you're normalizing an amphibole, but in reality, the mineral is really a pyroxene or something. So there are a number of reasons why there could be something amiss there, but it's something to keep in mind. But in any case, we're going to do the calculation here for the charge balance, and this is a pretty straightforward calculation. It will be the sum of the negative plus the sum of the positive plus 3 times the amount of iron 3 plus, okay, plus 2 times the amount of iron 2 plus. And again, you can see that this number nominally ought to be 0 because there isn't any iron in this, but because of rounding error, it's a very small deviation from 0. But that is certainly within the realm of the precision that I need, and so I'm happy with that number. Okay. So this is our little section on the charge balance. I'm going to pause the video here, and then we are going to move on to the remainder of the site fillings. Now that we know what the iron 2 and iron 3 numbers are, even though for our first amphibole here those numbers are 0, but later on those will show up.